So now what are the different modes of transfer of heat? How the heat is going to transfer? So let's say there are various techniques, the thermal conduction, convection and radiation. So in that, the first one we are going to focus over here, the thermal conduction. So in case of thermal conduction, obviously let's say these are the two ends of a rod which are at different temperature, or even you can say that consider this two ends. Yeah, so let's say for example keeping these two ends, so this is one end of the rod kept in a furnace and another end it should be in your hand. Yeah, so let's say this is a furnace where I am providing the heat. So this part first it will get heated, this is at temperature T1. Yeah, so obviously now what will happen in this case, the heat is going to transfer from one part towards another part, from this one end towards another end. So this molecule over here will receive the energy first, then they starts vibrating. Yeah, so they starts vibrating over here. Now at the same time they will give their energy to the next molecule, the next molecule also starts vibrating, so then they will give the energy to the next one. Likewise the energy will reaches up to the final one. Yeah, so definitely their energy has got increased, because of which the temperature also has increased. Now you can do one thing, so you can see, observe that if you just put the thermometer over here, let's say T1, T2 and T3, I just keep some holes over here. If I put some thermometer over here, this is T1, T2, T3. I found that the value of T1 is greater than that of your T2, greater than that T3, and then after certain instant of time this temperature constant, this T1 is fixed, T2 is fixed and T3 is also fixed. There is no further rise in the value of that temperature at that particular point. So that means they reached a steady state. They reach a steady state means there will not be any further rise in the temperature over there. So whatever heat they received, in that case they are not going to absorb, they simply some part of the heat get radiated and some part of the heat they will transmit. So they will not going to absorb any heat further, and that is what we can say. So they achieve the state of steady state over there. Similarly the same thing over here I had just shown over here. So this is T2 is greater than T1, so there has to be some material medium for the flow of heat. Yeah, and which is flowing from one end towards the another end. So there has to be some physical medium to be present in case of this first mode, that is nothing but the thermal conduction over here. So which I have shown, so where the molecules are just vibrating about their mean position, there is no actual movement of the molecules will occur, but definitely after a certain time all of them will achieve the steady state over here. So this is how we can define this your thermal conduction. So now for this case also we can define one more case. So this flow of heat transfer, so this heat transfer for this particular case we can write it down. So this H, yeah, so this two ends, so there is a flow of this heat between these two ends. Yeah, and there has to be some cross sectional area. So this heat is proportional to, let's say this is Q is proportional to obviously dt upon dx. Again this is proportional to your area dt by dx. Again this is the amount of time for which the heat is going to flow over here. So this one you can say that Q is equals to Ka dt upon dx into T. So the amount of heat flows is proportional to the cross sectional area, then it is this cross sectional area, so which I have shown over here. Then the difference in temperature of these two ends, so let's say the temperature T1 T2, if the temperature difference is greater, then that is also the amount of heat flow is also greater than the time for which your that heat is going to flow. So this K is called as a coefficient of your thermal conductivity. So this is how we can just define, this is a formula, and the rate of flow of heat also you can write it down, Q upon T, that is a Ka dt upon dx. So this is again a very important expression for the rate of flow of heat. Now let's see what is that heat current and thermal resistance for this particular case. So we know that, so obviously V is equals to IR, that we will just now compare it with your electrical analogy. So where the current flowing through a conductor, so we can say that is I is equals to V upon R. Now similarly, if we just consider for the case of this transfer of heat, the transfer of heat from one end to the another end, so why this heat transfer will occur? So likewise, in case of your flow of current, we can say that if there is a potential difference between its two terminals, yeah, so then there is a flow of current. So the heat will flow mainly because the difference in the temperature at the two ends. So this delta T is responsible for the flow of heat, and we have seen that this Q is equals to, or Q upon T, that is a Ka dt upon dx. So this dt is equivalent to now your, that is voltage. Now this Q upon T, that is the rate of flow of heat, so which is nothing but I. So this is similar to your, this is what we can say about your I. So this delta T now. So again, if we just consider that, then what is the resistance? So this V is equals to IR. So this V is nothing but, again for example, that is a delta T, then this is Q upon T. So we can take it on this one side for this particular case. So let's say this V upon I. So I can just consider this dx upon Ka, which is nothing but dt, then multiply by T upon Q. So this dt upon Q by T over here. So this dt is nothing but equivalent to your voltage. So this is nothing but your voltage, okay, and again upon current. So this is nothing but the resistance will be dx upon Ka. So this dx upon Ka is nothing but equivalent to the thermal resistance. So this is the value of your resistance, which is the length of the conductor upon the coefficient of your K, that is the thermal conductance, into cross sectional area for this particular case over here. So that is the analogy how we can just correlate the heat current and obviously that your electric current, and we can find the thermal resistance over here. So let's say I will just denote it by RT, so which is nothing but your thermal resistance over here, and it is given by the formula of your dx upon Ka.